Hey everybody! So today we're going to learn about population ecology. So populations, just for a definition, is individuals of the same species occupying a certain area. So you can describe populations with the size, the density, how it's distributed, if it's clumped or if it's spread out evenly, and then age structure, which would be, what percent are different ages in the population. And individuals tend to mate with other individuals in the population rather than different populations, so there's low gene flow. If you are, let me move my picture. So populations have adaptations for using energy in an environment. So the size of a population depends on the resources that are available. So if you have low resources, you're going to have a small population. Reproductive rates are going to be low, and the offspring don't survive well because they don't have enough food or water or habitat. On the other side, if you have lots of resources, you're going to have a large population, you're going to have a high growth rate, and those offspring are going to survive better. So they have different ways of adapting to when resources change. So birds, as we know, and other animals fly south and they migrate, or like bears hibernate and other animals hibernate in the winter and they store fat so they can conserve energy. So this is just a full picture of a penguin population. Yeah. So reproductive strategies are also an adaptation to the environment. So the two that you are going to need to know are what's called R selected species. So R selected species tend to, it's like a fish, tend to have lots and lots of offspring, but they're very poor quality. So they're not looking for all of them to survive. They're looking for a few to survive. And so you have low quality, high quantity. And these organisms usually live in unstable environments, so it's beneficial for them to have lots and lots of babies. And they also don't spend very much time parenting. So that's an unstable environment, lots of offspring, low quality, and low energy in parenting. So that'd be like fish or spiders or I don't know, anything, insects, right? And K-selected species is the opposite. So they have few offspring, they spend lots of time parenting, and the offspring are good quality, and so they survive. And an example would be deer. We are K-selected, elephants, any of those. So we're going to talk about some ways to calculate growth of populations. So with this one, you have your equation sheet, and you'll see, if you look at growth rates, you'll see this equation right here. Sometimes people talk about delta N, like delta means change. So I just wanted to make you aware that these two, delta N, delta T, is the same thing as this D that's italicized. It's just they couldn't probably print a triangle. So this would be the change in population size over a certain amount of time is equal to your birth minus death. So those things are here, and these equations are on your equation sheet. If we're talking about exponential growth, which is a J-shaped curve, then we are looking at the R max, and this is the intrinsic rate of increase or the per capita increase. So per person, and population size is N, you would multiply these two to see how much the population grew in a year if it was exponential growth. So we're going to do some calculations. So I'm going to have you pause at certain points to be able to see if you can do the calculations by yourself, and then we'll go through them. So first one is calculate a population growth in one generation if births are 600 and deaths are 100. So go ahead and pause the video. Okay, so you should have used this equation. That's the first thing you want to do is figure out which equation to use. So we want to know what the population will grow in 1 year. So we're going to take your births minus your deaths, and that's 500. And so this population will grow 500 in 1 year. Okay, so here's another one. So calculate the population per capita growth rate. So we're looking at our max if the births and deaths are the same as above, but now the population size is 8,000. Okay, so go ahead and pause the video. Okay, so first you need to think about which equations you need. So the two equations that you should use are this growth rate one and also the exponential one. Something you should remember back from algebra probably is when two equations are equal to the same thing, you can set them equal to each other. So you know births, you know deaths, and you know population size. So if you set those two equal to each other, you can find our max. And so you just do the math, and this is your answer right here, 0.0625. So that is your intrinsic growth rate or per capita growth rate. R max will always be less than 1. The bigger the R max, that means the population is going to grow faster. So that's just a good way to check your answers. Okay, so this same population, what will it be after 3 years? So this is a little more tricky in how you do this. So go ahead and pause the video and see if you can do this. Okay, so you have this equation, right? Change in population over time equals R max times the population size. So it's not as easy as just dividing by 3 because your N is going to change each year, right? Because you keep adding individuals to the population. So the first year, because you do it by year, that's why you divide by 1, you're going to have your 0.0625 times 8,000, and we did this before, and that gives you 500 individuals that first year. So after 1 year, the population would be 8,500. In year 2, you would take your growth rate, 0.0625, multiply it by 8,500, and you get an additional 531.25. So you're going to add that to the 8,500. And the final one you do is the same. So our max doesn't change, it stays constant. The thing that's changing is your population size. And so you add that additional people to your population, and then you get this much got added for the third generation, and then you add that. After 3 generations, you should get 9,595, and if you round it, it would be 96. Okay, so the key things to remember here is that you can't just multiply it by 3 because it was 3 years, because the population size, N, somebody explained it's like interest. It changes every year. So you gain a little bit, and then you need to multiply it by the growth rate again, and so that's why it's not going to be an even 1,500 after 3 years. Okay, so exponential growth looks like this. It's a J curve, and R is going to, if the R is positive, if R max is positive, it's always going to grow exponentially. Okay, and the larger the population gets, the more individuals are reproducing, and that's why your slope is larger. So if R was larger, right, if R max was a bigger number, so let's say this is, I don't know, 0.08, maybe we want to know what 0.2 would be, your line would be on this side, and it would go like this. It would still end up becoming exponential. However, it would start that quicker. If your R max was smaller, then it would take longer for it to become exponential, but then eventually it would. Okay, so some factors limit population growth, right? Populations don't just grow exponentially forever because there are limiting factors. So there's 2 types. One is density dependent, and those can be abiotic or non-living, or biotic, and they're factors that affect population size because of density. So for example, the bigger the population, the more dense the population, food is going to become limiting. Habitat's going to become limited. Mates limiting. Disease spreads faster in populations that are more dense. All these things are going to limit how big a population can grow, and they're all um, going to decrease it. Density independent can also be abiotic or biotic, and they affect the population regardless of what the density is. And I always think of this as natural disasters. So a flood is going to destroy a population, whether it's 5,000 or 500, right? It's not going to destroy a 5,000 population more than a 500. A forest fire, a volcanic eruption, it doesn't matter how big the population is, they're going to be affected the same way. And also pollution is density independent. So the carrying capacity is the maximum number of individuals that can be sustained in a particular habitat. So with the food and resources and mates and all that stuff, it's the max number of individuals that can be sustained. And so it would be something like this when your logistic growth flattens up. So the logistic growth model from A to B, right, starts out slow because there aren't very many individuals, and then it goes into exponential growth and finally levels out at the carrying capacity. Sometimes populations exceed their carrying capacity, and then the limiting factors will bring it back down. So that's why sometimes you see it fluctuating around the carrying capacity, which would be this line. So like I said, sometimes populations overshoot and can go above the carrying capacity. So here is the carrying capacity of these reindeer, and they went above. And what happens is it's usually followed by a crash in the population. So for example, if you had a bunch of deer in a certain area, reindeer, and they ate the grass, instead of just eating the grass to a certain point where it could grow back, they may eat it to the point where it dies. And so then the population, if you look back at this one, then the population would be, the carrying capacity would be even lower because some of their food is not regenerating and is not coming back. Okay, so that is the logistic growth. And there's another equation for that on your equation sheet. And it looks like this. So if you are ever given the carrying capacity, right, then you know you need to use this equation. So what you do is, let's say that you have a population that's experiencing logistic growth. Calculate the population growth rate, which is the number of individuals added. So you're calculating this really, and your DT is over one generation. So let's say your population size is 500, your Rmax is 0.12, and your carrying capacity is 800. So you're going to use this equation, go ahead and plug everything in and see if you can find out how many individuals will be added after 1 year. So go ahead and pause the video and try the question. Okay, so you should have, if you look at you should have plugged the numbers in like this, and you should have gotten 22.5 individuals added each for the first generation, right? Now, if you got a really hard question, then maybe you would substitute this 22.5 and you would add it to 800, or no, I'm sorry, to 500, and do it again to find out what the population growth would be the next year. But I've never seen a question that's that hard. And that's it. So hopefully you learned something about some more math that happens in ecology and how populations grow. And we'll see you next time.